Let us consider a DC generator. Now, the parts of the DC generator are pole and the armature. Let us say P is the number of poles on the generator. I am considering one conductor which is moving from position 1 to position 2, which means that the conductor is moving under the north pole. If phi is the flux per pole, when this conductor moves from position 1 to position 2, it is linking with, or it is cutting the flux of phi given by the north pole. Next to the north pole, we will have a south pole. So when the conductor moves in the clockwise direction, what I have shown from position 2 to a new position under the south pole, it also cuts the same amount of flux. If there are P poles present on the machine, all the P poles are symmetrically arranged. Therefore, in one revolution, each conductor, that is the conductor what I have considered here, will be moving under all the poles. Therefore, it will be cutting a flux of P into phi. Let us say N is the speed in revolutions per minute. The speed in revolutions per second will be revolutions per second is equals to N upon 60. Therefore, time for one revolution, if I write this as delta T, is equals to 60 upon N. In one revolution, delta phi, that is the flux linking with one conductor, it will be equals to P into phi. Then EMF induced in the conductor is equals to delta phi divided by delta T. I call the EMF induced as E. So this gives us P into phi divided by 60 upon N. So this gives P phi N upon 60. This is the EMF induced in one conductor. If there are Z conductors present on the armature, that is, Z is the number of conductors present on the armature, and if all the conductors, all the Z conductors are connected in series, then the EMF induced in Z conductors is given by EMF induced in one conductor multiplied by Z. So this will be multiplied, the voltage induced in one conductor will be multiplied with the number of conductors to give a larger amount of voltage. But what happens in the generator is, all the Z conductors, they are not connected in series. Okay? These Z conductors are connected in a number of parallel paths, each path having Z upon A conductors in series. So this gives us the induced EMF E is equals to P phi N upon 60, that is the EMF induced in one conductor multiplied by number of conductors in series in a parallel path. So if I simplify this, I will be getting an expression as phi z n upon 60 into P upon A. In DC machines, say in the DC motor or a DC generator, it is possible to connect the Z conductors in two types. One type we call it as a lap winding, for which the Z conductors are connected in number of parallel paths equal to number of poles, which means for lap winding A will be equal to 2 and equal to P here, and we have one more winding called a wave winding, for which the Z conductors are just connected in two parallel paths. So therefore, for wave winding, I get A is equal to 2. So based on this, if I replace A in this equation by P, I will be getting the induced voltage for the lap winding. And if I replace A by 2, I will be getting the induced voltage for the wave winding. I just give you the equation for the induced voltage in the lap winding, for which I have P phi z n upon 60. A is equal to P. Therefore, if I substitute P instead of A, I will be getting an equation phi z n upon 60. If the same armature is connected in wave fashion, then the induced voltage for the wave winding will be P phi z n upon 60, and for the wave winding, the number of parallel paths A is equal to 2. Okay. So if you compare these two equations, we have the term what I have here, phi z n by 60 will be the voltage induced for the lap winding. It clearly shows that wave connected armature for a DC generator will give you more voltage compared to lap connected armature.